Welcome everybody to CHC's February event. Today we have Western Hyperloop giving us a presentation, so I'll pass it off to them to take it away.
Bruce, you want to kick us off?
Yeah, thank you, JP. Thank you, Krista. All right, so yes, hello everyone, and welcome to our presentation on Trillium Hyperloop's design for our Flywheel test system. All right, so my name is Bruce Gillespie, and I'm the linear induction motor lead at Trillium Hyperloop. I'm just going to start by giving you a little background on who we are and how we got into Hyperloop and everything like that. So Trillium Hyperloop is Western University's Hyperloop design team, and we're also their newest engineering team. So we started around April 2020 is kind of when things started to get rolling and we started planning for the team. And then at the start of the 2020-2021 school year was when we started to kick things off and started really growing as a team. So yeah, it started as a group of engineering students who were really passionate about sustainable transportation. And we wanted to work towards competing at a Hyperloop design competition. So since we started back in 2020, we've now, so since we started, or if you could just go back a slide or two there, please. Wonderful. So yeah, since we started back in 2020, we've grown a lot as a team, and we've started to reorient our goals to focus on improving the Hyperloop community here in Canada, which is why we joined the CHC. And we're really proud of our progress that we've made. So we're going to be demonstrating some of that to you today. So I'm going to start us off by handing you to JP, our project lead, who's going to talk a bit about the Flywheel test system and what inspired us to use a Flywheel as a testing medium. Over to you, JP.
Great, thanks, Bruce. So for the Flywheel, we identified a few problems that were inherent in trying to test our design. So around fall semester this year, we were getting to a point where we were starting to feel really comfortable with our design. And we had to start thinking seriously of how we're going to test it out and make sure that it was going to work. And so Hyperloop test tracks are extremely expensive. You have to create the vacuum sealed chamber, and you have to set up the infrastructure costs, you have to maintain it, and then there's the real estate costs involved with it. And with SpaceX not running their Hyperloop competition, we were kind of left in a limbo. We knew that at that point in time, there was some rumor that CHC might be building a track. However, there was still a lot of uncertainty around that, where it was going to be made, whether it was in the Waterloo Airport, how would we transport things there. And it really put us in a tough position because we had designs that we wanted to test out, but we did not have any means of testing them. And in addition to that, if we wanted to test on a track, say CHC's track, there's no guarantee that the track would even be long enough for us to test out our full acceleration and our full braking, because we would require at least 100 meters of track. And I think even with the current implementation, it may not even be that long. So the longer the track, the better in terms of testing, so we could test our acceleration and our braking and all of that. So it was really important that we found a solution that was easily reusable and adaptable. It could be used for all sorts of different acceleration and braking speeds. So there's kind of like an indefinite limit on the track length. And then there should also be some ability for us to use it in the winter. It made sense in California, the way that the SpaceX team constructed it, because it's in a warm environment and it's also enclosed as well. So the aluminum I-beam is kept safe, and it's in a relatively warm climate, so there's less risk of there being some kind of erosion or some damage to the electronics. So winter conditions were also a really big factor as well. We needed something that we could be sure that we're not testing in the winter. We're not risking some of our electronic devices, especially in our development phase. So it could not be an open air track, or if it was an open air track, it would have to be modular and movable. So that provided us a very narrow constraint. Those provided us very narrow constraints as to how we would be able to test out our linear induction motor, our electrical systems, and our mechanical systems. And that's what led us to the solution to this problem. So the solution for us was the flywheel. So the really good benefit about the flywheel is that it can be run indefinitely. And so therefore you do not have to design the track to any certain amount of length. You just simply use the rotor and you put it on an axle, and you could attach your linear induction motor on either side and just spin it up to whatever speed you want, so you could test your acceleration. And then on the exact same thing, as you could see in the diagram at the bottom, you could just apply the brakes on it and test out your braking as well. And we're also considering additional optionality in terms of, spinning it up so without the use of a linear induction motor, so you could also test the braking. But my peers will talk about that after. But really what we decided was that really the big criteria for what we decided was that the flywheel was something that was going to remove a lot of the issues that were associated with tracks. It would allow us to test it locally. It would allow us to try swapping in different materials, maybe even try substituting different rotors. It would allow us to easily sub in linear induction motors and sub in different brakes, and it allows a really modular approach to testing that we really liked. So that led us to the solution. And so you can go to the next slide. So I'm going to be passing it off now, and we'll talk a little bit more about some of the problem parameters that went into the actual specification once we had the high-level idea of the flywheel, and how we went into the actual implementation of that. So take it away.
Thank you. So yeah, the main thing that we wanted to do here was that we wanted to create an environment that would be very similar to the water loop test track, just so that when we had our final model in place, we would have had a very good real life simulated piece to test and track. Essentially, we wanted to be able to collect data from these tests using our sensors, and we'd be able to apply our different systems just to create like a fail-safe model. We also wanted to make it easily modifiable, as JP mentioned. We wanted to have each of the systems and the components be removable and adaptable, depending on the different types of technology that we'd want to implement at different stages of the process. But we did note that we need to keep safety in mind, and this means that the flywheel system has some sort of safety or barrier on the outside. So we decided on an open air plexiglass casing that would surround the 4 exterior walls, just to prevent any sort of hazards or risks that would come into play, to protect both our components and our peers who'd be working on it. There would also be a very notable aspect where we looked at system redundancy to remove potential failures, meaning that we did have a booklet or a manual that prescribed all the safety requirements that be put into place in order to protect our entire pod and the components that be going onto it. There's also a temperature modulation system that we had planned. So this includes cooling and potentially even fluid coolant that be added to it in the future, depending on the temperature requirements at that point. However, the current flywheel model has just an open air top, which means that it would have access to free air movement. There's also an operation manual, as mentioned before, that just outlines any sort of safety requirements. So this is just the flywheel schematic. On the left-hand side, you see an image where there's a piston model. This just allows for better damping of the flywheel. However, the final flywheel will just include a single axle through the middle. And on the right-hand side, this image just shows the placement of where the braking and limb can be tested. I'll be passing it off to my colleague to just talk about our iterative process and how we came up with the first design.
Matt, I believe you're muted.
Thank you. So I was just saying, there was a lot of things that we really kind of liked about our initial designs. The piston design there, as mentioned, it provided good damping and it provided a lot of really good vertical support for the flywheel. And we also kind of liked the way that we were kind of easily able to mount the our linear induction motor and our brakes to our design. However, we also had a few issues. So because we were mounting a flywheel in a vertical orientation, obviously I had a fairly narrow base, and so it was a lot more susceptible to tipping than it would be in a horizontal orientation. And also this kind of required a really large area of caging just to ensure that no one was able to, touch the flywheel or anything while it was in use. And it was also, we kind of found with the way our design was, it was difficult to change and move components as we were changing design. Obviously, like our limb, our brakes, everything is kind of still being worked on. So we didn't want to have to go back and redesign our full flywheel system every time we made a change there. So that's kind of what's been leading us to our second design. So as you can see here, we've moved to a horizontal oriented flywheel rather than the vertical orientation we had before. Offers some improvements to stability, and also it allows it to be much easier to cage as it's a much smaller area of caging needed. Also, we're now using a large concrete base, which is very useful as it provides a very heavy, stable platform to support all of our components. And it also really easily allows us to mount any hardware or anything like that we need to attach to it. And because we'd be casting this base ourselves, we'd even be able to do things like put in our own sort of cable channels to keep any cables away from any of the moving components. As you can also see, we have a welded steel frame that surrounds the entire flywheel. And in some of the pictures, you can kind of see in the back there, we were looking at using a mesh grating rather than the plexiglass that we thought about before. However, we're kind of still making the best decision on that as to what offers the best sort of protection while still allowing the best airflow and stuff like that. But yeah, so that's kind of the major changes. If we move forward, we can kind of show some of the testing that we've done so far. So obviously, one of the major concerns with a large, fast-moving disk is the stresses generated within it. So before we even started any of our flywheel designs, one of the first things we did was wanted to see how fast can we reasonably go to without compromising the safety of our design. So here we performed some stress analysis just to see how the material would be able to handle. And we found that we were able to go up to a speed of about 1,000 kilometers an hour while still maintaining a factor of safety of about 1.5. So realistically, for a very long time, we're not going to have to worry about our flywheel exploding. But actually, to further validate this, once we had a CAD model of our design, we even performed some FEA analysis, and that's on the next slide. So as you can see here, we actually were well below about, we have a factor of safety of about 2, actually quite a little bit more than that. And so there's really no concern of the flywheel damaging itself from the speeds that it's traveling at. Now, another concern that we had was obviously, this is a very large flywheel. It's about 1 meter in diameter. And so we were kind of concerned about the stability of our frame and such. So we performed some analysis there just to make sure that all the components mounted to it won't cause enough deformation to impact the usability of the design. And from this analysis, after adding some stiffening members across the top, we have the deflection down to less than about 1/8 of a millimeter. And so realistically, that's well within reason and something that we are well able to compensate for. So now I'm going to pass it off to Ahmed, who's going to talk a little bit more about some other analysis that we've done.
Hey guys, so like every mechanical engineering design, heat transfer or thermal analysis is very essential. Given the fact that we're going to operate our brakes and test our brakes within the same schematic as our linear induction motor, we have to make sure that the heat generated through braking does not impact the integrity of the components within the linear induction motor, because it is costly and it's not something we can easily reuse or rebuy. So the first thing we did was we wanted to calculate the overall heat generated through braking. So essentially this was done using momentum conservation equations with impulse, braking time using 2 Gs of force. And from there, we calculated that the overall generated heat is 9.38 megajoules, which over the span of the braking it will increase the flywheel temperature to approximately 630 degrees Celsius, which is obviously extremely high. However, given the speed of the flywheel, which is approximately 1,000 kilometers an hour, and the open ambient air it's exposed to, this allows for a lot of convective heat transfer cooling, which does play hugely in our benefit. So to confirm that, we want to make sure what would the final temperature of the linear induction motor be. And using basic heat transfer analysis of radiative heat transfer and conductive heat transfer to the actual radius of the flywheel, and then convective heat transfer to the linear induction motor, the result came out to be that the final temperature of the linear induction motor will be 32.6 degrees Celsius, which is way below the maximum operating temperature of the metal components within a linear induction motor. Now, these are very conservative calculations, and also thermal analysis in general has a somewhat of an uncertain analytical approach. However, this is why we will implement a sort of external cooling system, as Yamini mentioned, which will just literally be a pipe that kind of shoots out cool air kind of into the flywheel schematic, and that will ensure the linear induction motor will remain cool and the components will not be damaged. Thank you.
All right, thank you, Ahmed. So with any system, safety is a major factor that needs to be considered. And with ours, we decided to do a safety analysis on the flywheel system to identify the hazards that will be present when we're operating it and figure out the ways to best mitigate them. So as you can probably guess, the main hazard of our flywheel system is the giant spinning aluminum disc. So this can be very dangerous if it's not properly contained, and we wanted to do a few things to protect ourselves and anyone else who's using it. So to ensure that no one can touch the flywheel, as Matt had mentioned, we're going to be implementing a wire mesh around the outside of the enclosure. Now this will, first off, enclose the flywheel, preventing anyone from touching it by accident, or if something falls on it during the operation, it won't fall into the wheel and damage that or any of the components inside. So that's the first thing. But the reason that we chose the wire mesh was also for the air circulation. So the wire mesh will not only prevent contact with the wheel, but also allow any airflow to get in as we need. Now, as a structural support, we're going to be using extruded aluminum beams around the outside of the flywheel, which will support the limb mount, the bearings, and the braking system. Now, on top of that, this aluminum frame will also serve as like a containing feature for the flywheel. So in the worst case scenario, if something were to come unbalanced, or for example, like the limb were to come loose, the extruded aluminum frame, in addition with the mesh, we're predicting would contain all the components, which is what we want. So as Ahmed mentioned, the flywheel will heat up a lot during its operation. So we need to make sure that before we work on the flywheel after its operation, or before we change out any parts, it's cool. Because again, as Ahmed mentioned, it won't damage the components within the enclosure. However, when it heats up during that braking stage, it could cause burns to someone who's working on the flywheel. So to mitigate that, inside of the system, we're going to have some temperature sensors that will be able to measure the ambient temperature, as well as get an estimate on what the recurrent rotor temperature is. So this will be beneficial for us during our tests to understand how much the rotor is heating up, as well as indicate to the operators when it's safe to go inside the enclosure and when it's safe to touch the flywheel itself. So next, considering the high voltage current high current and high voltage that's going to be used in this system, we need to make sure that those are first isolated from human contact, easily identifiable, as well as positioned so that they won't be damaged by anything inside of the enclosure. So to do this, we're going to be wiring the linear induction motor and the braking system from both the top and bottom of the enclosure. And we're going to be trying to minimize any wires that are exposed within the flywheel area. So as Matt mentioned, we'll be able to implement a channel through the concrete base where we'll be able to feed wires through. So then what this will do is it'll minimize the amount of wire that's actually exposed in the enclosure, as the wires will be able to come up through the bottom of the concrete base, and we'll be able to connect them to the limb and to the braking system as well. Now that's from the bottom. However, from the top, what we'll be doing is, if you remember from Matt's diagram, there's some support beams that are running across the top. We'll be able to wire both the top side of our linear induction motor and the top side of our brakes over those wires. So we'll be connecting the wires closely with the beams and also labeling them in orange, making them easily identifiable, and also labeling them so that people will not touch them and they will not be damaged. So on top of identifying the hazards, we want to create a safety protocol document that we'll be providing to all team members who use the flywheel and any teams who come to use the flywheel on top of our own team. So what this will include is how to operate the system, what kind of risks are associated with the system, like some of the ones I just mentioned, and also what to do in an emergency. So I'm just going to share with you a few points from that document now, just to give you a bit of an idea on what's inside of it. So we talked about utilizing extreme care when handling the flywheel system. It's going to be a heavy system, so moving it will require some care as well. During testing, we want to make sure that no component is going to be removed or modified until the test is complete. We need to make sure that the flywheel reaches a complete stop before we open the system or modify it, or even start the next test. And we need to make sure that it's at a safe temperature before we actually go inside and make any modifications, as I mentioned earlier. Now, all access compartments are going to be closed and locked for each operation. So with this enclosure, we were planning to have some access panels, as we were calling them, where we could open up the cage door, get inside, work on the limb, or work on the braking system or anything like that, adjust anything as needed. But to prevent that from opening during operation, we're going to be locking those before the start of any test. And finally, all electrical components will need to be verified before each testing. All electrical connections will need to be verified before testing to make sure that they're complete and nothing has come loose during the setup. So these are just a few points of the protocol that we've created. But we'll be creating a full document that will be associating with this flywheel for training in the future. So next, I'm going to be talking through a bit of the cost analysis that went into planning our flywheel. So this is just a brief overview on the major components that we'll be using and our sources for them. So first off, the main component is going to be the aluminum disc that will act as the rotor for our flywheel. From there, we'll also be needing some very low friction bearings, which will allow us for accurate data collection. There will be two bearings, as seen in Matt's document or schematic, one on the bottom of the system and one on the top of the system, holding both sides of the axle. Next, we'll be using extruded aluminum as the frame supports to support the braking and limb system, as well as provide safety in the event of any damage that occurs during the operation. We'll be using the wire mesh to enclose the system, prevent anyone from touching anything and prevent anything from falling into the system, as I mentioned earlier. And finally, we'll be using a concrete base for the system. So again, the reason for choosing this concrete base is we want something heavy enough so that the system won't move during its operation, and also something customizable to our dimensions and something that will allow us to customize a channel for the wires inside of it, and also something that's budget friendly. So concrete provided all those things, which was great. And finally, it will allow us to drill the extruded aluminum and bolt things into the concrete, which will protect the floor of our workshop because our university doesn't want us drilling anything into the floor there. So this will provide an alternative to that. So overall, as you can see, our current estimated bill of materials is $2,355. This is before tax, and again, these are just approximate costs. But we'll be hoping to expand this cost analysis and get a more detailed analysis on the little components that'll be going along with it in the coming weeks and months. Now it's back to you, JP. Thank you.
Awesome. Thanks, Bruce. So just to really sum up everything that we've talked about today, we believe we've created a solution that is modular, scalable, and feasible. We've had the chance to speak with other teams, and concerns around tracks and being able to test out your pod is a really big concern for teams. So having a solution such that student teams can easily test out their linear induction motor, easily test out the braking system, easily test out their electronic systems is really vital for the Hyperloop community. It's really important that we have these kinds of solutions in order to test them, specifically in Canada. Otherwise, we can only test in the summer. It's good to be able to test year round. The Flywheel is a really great solution to that seasonal problem that we as Canadians are addressed with. So we think it can really help out. It could really help out the progression of Hyperloop research and student teams that are able to create really cool electrical systems and really try them out and start pushing the limits of this technology and see where it goes. We're open for collaboration with other teams that will want to use our Flywheel once we're done. So now that we're nearly done the design phase, we'll probably be consulting with some of the professors on our campus to talk about allocating space for this and figuring out the logistics of it, and then start looking into actually implementing it. So those are the next steps that are coming forward for this Flywheel design. Would also be happy to engage in conversations and discussions with other teams that might be interested in building their own Flywheel. We learned a great deal. We'll give a great deal of credit to EPFL. They had a presentation for their linear induction motor last spring, and that was a fantastic presentation. It talked about their linear induction motor and how they use the Flywheel. We reached out to them. Although the back and forth was a little spurious, we nonetheless got a lot of inspiration from them. And it was a really big motivating factor for us as well. So shout out to EPFL for that. So we're pretty excited about this, and that pretty much concludes our presentation. I guess we could open it up for questions now. There's one more slide in case anyone wants to contact us. Please feel free. We're available over email, or you could find us on LinkedIn, Facebook, or you could reach out to us on our website. So thank you very much, and we're open for questions now.
Thanks, guys. That was awesome. Does anybody have any questions right now? You can just turn on your mic and talk, or you can type in the chat. I have a question. So you mentioned that the Flywheel will be about 1 meter in diameter. What is the benefit of having it be that big? Is it possible to make one smaller that could do the same thing, or not really?
Well, the main goal of having the Flywheel be those dimensions is because the parts that we're making, we wanted to make them almost real to life, or scale them down from what we'd be having on the actual pod. So having it be 1 meter in diameter was necessary in order to fit components like the limb and the braking, just to be able to simulate what would be actually happening on the pod. Yeah.
Okay, awesome. Cool.
One more thing on the note of just scaling it down, I thought it'd be interesting to mention. We've been working a lot recently on a prototype of our linear induction motor, and one of the professors at our university had a small scale aluminum Flywheel, which is a lot more scaled down, I believe, a diameter of about 6 inches. So quite a small Flywheel for our limb, but our prototype limb, luckily, is a lot smaller than our full-size limb. So we're able to get a brief estimate on kind of how it will perform. But when scaling things up, we want to ensure that the full length of the limb can fit on the diameter of the Flywheel, just so that way we can have minimal losses in the flux and everything like that.
Cool, awesome.
Actually, I guess one other reason I would say is also for future proofing as well. One of the things we're designing our Flywheel for, like we're trying to design it to be able to handle speeds up to about 1,000 kilometers an hour. Our current limb design and stuff, nowhere near 1,000 kilometers an hour, but we don't want to have to be remaking a Flywheel every time we want to test something new. So we're trying to design something that we'll be able to use going well into the future.
Cool, that's awesome. All right, well, thanks, guys. That was awesome.